All right, hi everyone. Thanks for coming to talk two, or coming to or watching, whatever this is, talk two that I'll be giving here at NCNGT. So just in case they didn't watch talk one, I'll take this opportunity to once again thank Marcella and Ben for organizing this part of the conference and for the invitation to present some work. So the title of this talk is Symplectic Fillings of Lens Spaces, and I think to some extent it will stand alone from talk one, but I will assume that you watched that. We, at one point, will state the result that was sketched in talk one, and the main purpose of this talk is to apply that result, but presumably you could believe this application without seeing the proof from last time. Okay, so let's state our goal. So our last talk introduced this JSJ decomposition for symplectic fillings. More generally, we said that we can split a filling of a contact manifold open along a splitting surface of any genus. So the JSJ decomposition is the genus 1 version where we have a mixed torus. So our goal today in this talk is to use that result that we gave last time, this JSJ decomposition for symplectic fillings, in the case of fillings of lens spaces. So we want to complete this classification problem, this classification of fillings problem, up to diffeomorphism. So we can start with a little bit of history of this problem. So eons ago, in the 90s, Eli Ashberg showed that the unique up-to isotopy tight contact structure on S3 has a unique exact symplectic filling. I didn't write down what this is, but I guess we gave it as an example last time. It's the 4-ball with its standard Liouville form. Now, today we're only going to work up to diffeomorphism, so you could take this as saying any exact filling of the 3-sphere is diffeomorphic to the 4-ball. Eli Ashberg showed something stronger, but we will just work up to diffeomorphism today. Okay, so then once the 3-sphere is settled, you think about more complicated, topologically that is, 3 manifolds. Well, if you like to organize your 3 manifolds by Heegard genus, then the very next thing after the 3-sphere is lens spaces. So we can think about contact structures on lens spaces. So every lens space admits a tight contact structure just by as a quotient of S3. So if you take the standard contact structure on S3, it's going to be equivariant under this natural action by which you quotient to get the lens space. And so it induces a tight contact structure on LPQ. So you could try to classify those contact structures, I'm sorry, the fillings of those contact structures. And indeed, Liska succeeded in doing so. So in 2008, Liska gave a full classification of up to diffeomorphism of the symplectic fillings of the standard contact structures on lens spaces. Once again, this classification is probably up to something a little more than diffeomorphism, though this one is typically stated just as up to diffeomorphism. And we would be remiss not to mention that McDuff had settled a large class of lens spaces much earlier, in like 1991. McDuff showed that the standard contact structure on LP1 has a unique exact, let's say, filling, unless P is 4, in which case there are exactly 2 fillings. Okay, so the standard contact structures, we will call them, were classified by Liska in 2008. But in general, there are lots of tight contact structures on a lens space. The number is precisely known. It's given by this product where these coefficients A0 through AN are determined by a continued fraction expansion. So for most lens spaces, there are a lot more than just the standard contact structures, and we'd like to classify the fillings of those non-standard structures. And here, plenty of results exist before the one we'll present in this talk. Most notably probably is Pomanovskaya and Edward Morris, who showed that LP1, actually any of its tight contact structures admit a unique filling class P is 4 and is a standard structure. So we want to today think about the fillings of non-standard structures. So we can give an informal statement of the classification, and I mean, to be clear, I'm using this adjective informal. This is the only statement I think we're going to give. It's not going to get more precise in this talk. So we'll say that every exact symplectic filling of a Lin space can be obtained by starting with an exact filling of a connected sum of Lin spaces and attaching two handles. So this is maybe not the prettiest way to say the thing, but if you start with LPQ with any tight contact structure, it has to be tight since it's fillable. Well, then you can write this as the filling of some, let's not even try to come up with integers, but just say L1, C1, connect sum, L2, C2, some filling of this connect sum plus two handles, where each of these context structures is standard. And since these are standard, well then this classification is done by Liska and Eliashberg's result for fillings of connected sums. Okay, so we'll give an algorithm for starting with a filling here and decomposing it in this way. And a corollary of this result is that every symplectic filling of a Lin space is diffeomorphic to a filling of a standard Lin space. That's because the way we attach these two handles matches what we would do up to diffeomorphism if C were standard. So basically the attaching data for these two handles up to diffeomorphism does not care what your contact structure is. And thus, this filling is diffeomorphic to a filling of LPQ with a standard structure. The only data that C gives to this two-handle attachment is at the symplectic level. So to diffeomorphism, we're good to go. So that's a nice corollary, which basically says this somewhat complicated list of fillings that Liska gave is in fact all fillings of all Lin spaces up to diffeomorphism. And I also must point out, happy to point out, that this result, which was obtained with Youlin Li last summer, was independently and simultaneously obtained by John Etnyre and Agniva Roy. And Agniva and John, their paper, I think, has a much richer discussion of some of the ramifications of this result and some of the interesting three-manifold topology that's there. So thankfully, Agniva is also, I believe, giving a talk in this session. I hope it's about this result so that I can continue to learn more about it from him. Okay, so what's our roadmap for the rest of this talk today? Well, we'll first recall the classification of tight contact structures, so how we came up with that count, which was given by some continued fraction thing. Once we have that list of tight contact structures, then we will actually apply the JSJ decomposition to obtain the classification that was just stated. And then at the end, we'll have like one slide where we try to discuss a diagrammatic calculus, which maybe is the fun thing about this result. We can break down our fillings using these cute diagrams. All right, so let's start with some history from like 20 years ago. Classification of tight context structures on Lin spaces. So to start, recall that every Lin space naturally bounds a smooth four manifold. Here's your proof, is that we can just attach two handles along these unknots, this simple link of unknots with the given framings. And these framings are obtained via this sort of backwards continued fraction. Backwards just because we're using minus signs, I guess. So you write out negative P over Q equals this. There's a unique way to write this continued fraction that has all of these framings less than or equal to -2. And then those are your framings. You can attach two handles and you have a Lin space. So that's how we'll think of Lin spaces today. This the size of the framing matters in the context setting, because now we can put a context structure on our Lin space by first putting each of these unknots into Legendrian position, and the Thurston Bennigan number will differ from the framing by 1. So each of these knots will now look like some sort of front projection. So this will give us a Legendrian surgery diagram for our Lin space. We can then, instead of just attaching smooth 2 handles, attach Weinstein 2 handles to the standard 4-ball along each of those Legendrian knots that naturally has a -1 framing for geometry reasons, and in this way we get an exact filling of LPQ. Okay, so we have an exact filling, the boundary is LPQ, this gives us a tight context structure on that Lin space. So up to Legendrian isotopy, we have some number of choices of Legendrian unknots that have the desired framing, and that number being this absolute value of a sub I plus 1. So we've thus produced absolute value of a sub I 0 plus 1 times a sub 1 plus 1 up to a sub n plus 1 fillable contact structures. I can't claim at this stage, I guess, that they are distinct, but Giroux and Honda, a little over 20 years ago, independently showed that these are in fact distinct up to isotopy, and they give you all tight context structures on this given Lin space. So there's our full classification of the tight context structures on Lin spaces, is that they're all in this nice diagram, this Legendrian surgery diagram. So now we want to classify all of those. But first, why don't we see a picture with an example of this classification. So here are the 9 contact structures on L24/7, 9 tight contact structures. So since -24/7 has this continued fraction expansion, -4, -2, -4, that means there are 9 isotopy classes of tight contact structures. And you can see, we have, corresponding to the -4, we have an unknot which has been stabilized twice. Corresponding to the other -4, another unknot which has been stabilized twice. And to the -2, an unknot which has not been stabilized at all. This is why it's important that the framing be at most -2. So then we have 3 choices for how to arrange the stabilizations on, say, the first unknot. You could make them both positive, both negative, or mixed. And then by considering all the different configurations there, we get 9 total tight contact structures. Okay, so some of these are universally tight. So the first and last here, where all of the stabilizations in our diagram across all knots all have the same sign. So in this first picture, they're all positive, and in this last picture, they're all negative. So these are the universally tight contact structures. One of them is the standard contact structure. I probably don't even want to decide which one it is right now, because up to maybe an orientation reversing diffeomorphism, it doesn't matter. So these universally tight structures, they are the manifolds whose fillings were classified by Liska. So then what we want to consider are all the virtually over-twisted contact structures, which are, in this case, the remaining 7. So we're going to especially focus on these cases where we would say that each of the knots is universally tight, in the sense that each knot has stabilizations of only one sign. But we don't have a universally tight diagram, because there is a mixture of signs. The reason we care about only those is that these others, we can apply a result of Minky pretty directly to knock those out quickly. Okay, so let's recall what this symplectic JSJ decomposition is. So it tells us that if we can find a mixed torus in our contact 3 manifold, then we identify a normalized embedding for it, which has slopes -1, infinity, and S2. And then we can split this open by removing a round 1 handle, and the result is a filling of some new contact manifold obtained from our original by splitting along T2 with some slope between 0 and S2 minus 1. Those are a lot of words. Hopefully some of them are familiar from last time, but the keys, of course, will be mixed torus, normalized embedding, and then we want to split with some slope. So now we need to identify mixed tori in virtually over-twisted lens spaces. Well, if our diagram includes a knot with both positive and negative stabilizations, then we can actually obtain this mixed torus pretty immediately. So as soon as you identify that one knot, because of some sort of correspondence between stabilizations and bypasses, and then a correspondence between bypasses and basic slices, we're able to look at this surgered manifold and identify a mixed torus and it split open along that mixed torus. And essentially what the JSJ decomposition tells us to do is erase this twice stabilized knot, the knot that's been stabilized both positively and negatively. And when you erase it, you're left with some other lens space. And every filling of the lens space that we cared about originally is obtained from a filling of this new lens space by adding in a 2 handle along the twice stabilized knot. And I suppose I should clarify, erasing this twice stabilized knot does not always give you a lens space. It might give you a connected sum of lens spaces if it sits in the middle of our link of unknots here. Then it would sort of disconnect that link. Okay. So then the case that's not covered by Minky's result, and Minky's result, which I didn't state precisely, it applies to any contact manifold obtained by surgery on a Legendrian which has been stabilized both positively and negatively. So we have some lens spaces to which that does not apply. And these are the ones where we have each knot with stabilizations of only one sign, but we have some mixture of signs in the diagram. So in this case, we're going to identify some knot K plus and some knot K minus in our diagram. We require that these be adjacent in the sense that there are no stabilized knots between them. So maybe they are separated by some number of knots with no stabilizations, as happens here. But there are no stabilized knots between them. So K plus is to the right of K minus, just without loss of generality. I mean, the argument works the same. K plus has only positive stabilizations, K minus only negative, and there are no stabilizations between them. So if we can identify this, then we reach back to sort of the details of Honda's classification of tight contact structures on lens spaces. And Honda allows us to write our lens space as a solid torus plus a thickened torus plus a solid torus. So this first solid torus, S0, is tight and has convex boundary with dividing curves of slope -1. The second solid torus, S1, is also tight, convex boundary, and this time the dividing curves have slope infinity. Honda then gives us a recipe for decomposing this T2 cross I, this thickened torus, into a number of basic slices. And in particular, these basic slices will decompose, will group into continued fraction blocks, it calls them. And each knot in our diagram for the lens space will have a corresponding continued fraction block. So we'll have a block here for K plus, and we'll have a block here for K minus. And I lied a little bit. Only the stabilized knots have continued fraction blocks. That's why K plus and K minus have adjacent continued fraction blocks here, because there is no stabilized knot between them. And the corresponding basic slices will have signs given by the signs of the stabilizations which have been applied. So having unstabilized knots in between these two adjacent knots will change the precise slopes that appear here, but they won't change the number of basic slices or anything like that. But the point is, because we have adjacent knots with opposite sign stabilizations, we obtain adjacent basic slices with opposite signs. So that means this slice in between them is a mixed torus. And we automatically get a normalized embedding. Well, it needs to be normalized, but we get this nice neighborhood with a positive on the right and a negative on the left. So then the magical thing that happens now is via some little arithmetic that can be done and is done in the paper, we can always normalize this embedding so that we have -1 opposite the minus basic slice, infinity for our slope on the mixed torus, and then m plus 2 will be our sort of free slope, which in this case is 3, because m counts the number of unstabilized knots between k plus and k minus. So this will happen every time, and this really just amounts to getting into the nitty-gritty of Honda's classification and then doing some arithmetic and some change of coordinates on the torus. So we'll have -1, infinity, and then m plus 2. Okay, so now the consequences are pretty immediate. Let's run through them. We now have this mixed torus sitting inside of our lens space, and it has a normalized embedding with S2, this free slope, equal to m plus 2, the number of unstabilized knots plus 2. Symplectic JSJ then tells us we should split that lens space along T with slope S between 0 and m plus 1. Doing so, one can check, will always result in a disjoint union of lens spaces. So essentially, well, we'll say what this means diagrammatically. You can check that just topologically, if you split open with a slope in this range, the result is a disjoint union of lens spaces. Now, these lens spaces have some contact structures on them, naturally, and maybe those disjoint contact structures are virtually over-twisted. If so, repeat the process, and we keep going until we end up with only universally tight lens spaces in our disjoint union. Okay, so now the JSJ decomposition directly tells us that we start with a disjoint collection of fillings of standard lens spaces, or universally tight lens spaces, and we attach a sequence of round one handles. The round one handles are one handles followed by two handles. So attaching those one handles, not yet the two handles, will sort of take our disjoint union of lens spaces, turn them into a giant connected sum, and then we're left over with two handles that can be attached to get the result that we find. So this proves the classification result we gave. And maybe in the last 90 seconds or so that we have, we can talk about the diagrammatic calculus that this yields, because these slopes give us a nice collection of outputs. So here's the lens space we started with, L24/7, and we have this m equals 1 because there's one unstabilized knot in the middle. And if we are considering this case where k minus is on the left and k plus is on the right, taking our slope equal to 0 corresponds to deleting k minus. And sort of when you get this disjoint union, sort of peeling off a copy of S3. So the way this decomposition works is we have S3 disjoint union, this lens space, whatever it is, you get a filling of L24/7 with this contact structure by attaching a round one handle along these two unnuts, or equivalently, attach a one handle, this connect sums S3 with this lens space, and then you're left to attach a two handle along this picture. So S equals 0 corresponds to, well, attach a two handle along this knot to this lens space. S equals 1 does the same thing, but for the unstabilized knot in between them. And S equals 2 corresponds to K plus. So when M is much larger, well, then you'll have a number of intermediate options, which involve just deleting these unstabilized knots in the middle. So the diagrammatic calculus can be extended, and then you just end up with this tree. All of these leaves are universally tight length spaces classified by Liska, and the deed is done. And I think that's a pretty fun way to end this talk. So once again, thank you to Ursula and Min for organizing. Thank you, viewer, for coming to the talk. Please come to office hours and post questions on Discord.